In science, we like to do our best to prove hypotheses. But just because it's not proven yet, doesn't mean it's not real. Take black holes. Carl Schwarzschild saw the possibility for black holes within the framework of general relativity back in 1916. John Michell, using Newtonian physics, hypothesized their existence even earlier, all the way back in 1783. But that means that for 55 years using relativity, or 188 years using Newtonian physics, we'd known about the theoretical possibility of black holes, but never actually saw any. The first black hole, Cygnus X1, was only spotted for certain in 1971. If it happened once, it's no stretch to believe it could be happening again. In the vast sea of scientific possibilities and outlandish ideas, exotic stars and strange forms of matter perhaps exist that are predicted, prolific, but are currently unperceived. What are these objects? Who knows? That's just it. They're unproven. But I and scientists around the world have a few ideas. I'm Alex McColgan and you're watching Astrum, and in today's Supercut we'll be looking at some of the strangest objects or states of the universe that could be real, if only we could find one to know for sure. Be sure to check back in after the next 188 years to see how many did turn out to exist. This video may not age well. Unsurprisingly, for astronomers, one of the first things we'll turn our gaze towards are stars. Stars are some of the most beautiful and awe-inspiring objects in the universe. Through violent thermonuclear reactions, they emit enormous amounts of light, illuminating the night sky and heating up any nearby planets in the process. Through mergers and powerful explosions, stars are also responsible for producing the heavy elements that make up much of the matter we see around us. Astronomers and astrophysicists have come a long way toward understanding how stars operate, to the point where we can even predict how long it will be before our sun runs out of fuel and transforms into a red giant. But today, we're not just going to talk about the types of stars we're familiar with. Instead, we're going to contemplate stars we've never seen before, ones that astrophysicists say could hypothetically exist, including ones that are quite literally made of vacuum. First, we need to lay some groundwork and understand how stars work in general, starting with the most important star of all, the Sun. Since the Sun is made of gas or plasma and not solid matter, you couldn't stand on its surface like you would on the Earth. The Sun's gravity would pull you down toward the center. So why doesn't the gas at the surface get pulled inwards too? It turns out that there is a pressure pushing outward from the Sun's core that counterbalances this pull of gravity. The main source of this pressure is the radiation created by fusion reactions in the core, the same radiation responsible for carrying light and heat from the Sun to the Earth, all directions. This radiation pressure wouldn't be enough to stop you from falling into the Sun, but it's just enough to stop the Sun's own gas, which is relatively light, from collapsing in on itself. This balancing act between inward pulling gravity and outward pushing pressure is a feature of pretty much all known types of stars. What differentiates different types of stars is where that pressure comes from. For our Sun, the pressure comes from fusing hydrogen into helium. When the Sun runs out of hydrogen in about 5 billion years, it will become a red giant star and begin to generate its pressure by fusing helium into even heavier nuclei like carbon and oxygen. Eventually, the Sun will also run out of helium and any other light elements that could be used for fuel for nuclear fusion. At that point, it will collapse into a small star known as a white dwarf. Since no more fusion is occurring anymore, white dwarfs are sometimes called stellar remnants instead of stars. But if there's no more fusion, where does the pressure to support these stellar remnants come from? It turns out that gravity pulls the gas of a white dwarf inward until it's so dense that a new type of pressure emerges, known as electron degeneracy pressure. This is a purely quantum mechanical effect, and it's the same effect that's responsible for you not being able to pass your hand through solid objects. Electrons simply cannot get too close to each other without an extraordinary amount of energy. But some stellar remnants are so massive that even electron degeneracy pressure isn't strong enough to counteract the pull of gravity. This is called the Chandrasekhar limit. It's absolutely impossible to have a stable white dwarf any heavier than 1.4 times the mass of the Sun. If a star has burned through all its nuclear fuel and its core is still heavier than the Chandrasekhar limit, that core will collapse in on itself until it becomes so dense that an even stronger type of quantum pressure emerges, known as neutron degeneracy pressure, which, as you may have guessed, prevents neutrons from getting too close to each other. A star that reaches this state is called a neutron star, the smallest and densest known class of stellar objects. So now you might be wondering, is there a maximum mass that a neutron star can have while still being supported by neutron degeneracy pressure? And there is. This time it's about 2.2 times the mass of the Sun. Any heavier than that, and the neutron star would keep collapsing under the influence of its own gravity until, well, actually, not until anything. As far as we know, neutron degeneracy pressure is the strongest possible pressure that ordinary matter can exert, so there's nothing left to prevent a sufficiently heavy stellar remnant from collapsing in on itself forever. This is the fate that might await some of the most massive stars we've observed in the universe. From the perspective of an outside observer, these stars would get so dense that all we'd be able to see is a black hole. That's a lot of pressure. But then scientists started to wonder, what would happen to a star that wasn't made of ordinary matter? If exotic forms of matter could hypothetically produce even larger pressures than neutron degeneracy pressure, then what new kinds of stars could exist? You might think that we could just continue the pattern that we were starting to see earlier. Stars could get even smaller and even denser than neutron stars, as long as they were supported by some even greater pressure. You might think that the only limit on how small these stars would get would be the point of no return, where they would turn into black holes. That point of no return is when a star becomes smaller than its own Schwarzschild radius. This is almost true, but not quite. Instead, physicist Hans Adolf Buchdahl showed in 1959 that a star made of any realistic form of matter with positive energy density and pressure can't be smaller than 9/8 times its Schwarzschild radius. It might not sound like a big difference, but that factor of 9/8 means that any realistic star has to allow for pressure to be negative in some regions and positive in others. Then Buchdahl's limit wouldn't apply, and that star would be less than 9/8 times its Schwarzschild radius. In fact, it could be arbitrarily close to the size of a black hole with the same mass. As a side note, theoretical stars like these that could mimic the appearance of black holes came to be quite a nuisance for astrophysicists, since now every time they discovered something that they thought was a black hole, they couldn't just say they discovered a black hole. They had to qualify that it's either a black hole or an extremely compact object mimicking a black hole, even though in their hearts most of them are quite convinced that it's a black hole. But back to the main point. What would these exotic stars with negative pressures even look like? The answer turns out to be even weirder than you might have guessed. Tolman, Oppenheimer, and Volkov derived an equation in the 1930s that describes how the pressure of a stable star changes as you go outward from its center. These days, it's just called the TOV equation for short. If the center of a star has a significantly negative pressure, which would exert some sort of attractive pull instead of a push, the TOV equation says that this star can only be stable and in balance with its own gravity if its pressure does something really wonky. First, the pressure has to blow up to negative infinity somewhere in the star. Then it has to flip sign to positive infinity and decrease outwards from there until it reaches zero pressure, marking the star's outer surface. The exact location of the infinite pressure depends on what the pressure is at the center. So if you tune that central pressure just right, you can keep the pressure finite right up until the edge of the star. That happens when the pressure at the center is exactly equal and opposite to the star's energy density there. In this special case, the TOV equations say that the pressure and energy density remain constant, equal, and opposite throughout the entire volume of the star right up until its surface. If you've seen some of our other episodes, this might ring a bell or two. A constant positive energy density paired with a constant but negative pressure. That doesn't sound like any star we've seen before, but it's starting to sound more like a mysterious component of our universe: dark energy. And since the pressure and energy density in a gravastar are equal in magnitude, it's not just any kind of dark energy. Those are the exact properties of vacuum energy. That's why this special exotic star came to be known as a gravitational vacuum star, or gravastar for short. Inside of a gravastar, there is precisely zero gravitational force, because the positive energy and negative pressure respectively exert a gravitational pull and push that cancel each other out. And since the pressure in gravastars is constant, there is no pressure gradient to exert any sort of push in one direction or another either. This means that if you found yourself inside of a gravastar, you would neither be pulled in nor pushed out. You could float freely, just as though you were in a real vacuum. Another curious feature of stars with negative pressures is that the closer you get to the special limit of a gravastar, which, if you recall, is when the infinite pressure surface gets pushed out to the edge of the star, the more their size approaches that of a black hole with the same mass. This raises two key questions that have recently gotten a lot of attention from physicists. First, how can we tell whether the extremely compact objects astronomers have observed in merger events and at the center of large galaxies are black holes or just exotic stars with nearly the same size? And second, if gravastars are real and scattered throughout the entire universe, then could they be the dark energy that's been making the universe accelerate for the past 5 billion years? To answer the first question, physicists rely on the main distinction between black holes and other compact objects, the existence of an event horizon. You see, the defining feature of a black hole is that nothing that falls inside or even touches the surface of a black hole can ever come back out. On the other hand, if an exotic star is even slightly larger than its Schwarzschild radius, it would not have an event horizon, and it would potentially be able to emit information outwards in the form of light. Not only that, but objects without event horizons could have different signatures in their gravitational wave emissions than those of black holes during a merger. This would allow us to tell them apart by measuring and analyzing those gravitational waves using observatories like LIGO. But even with this battery of tests, it turns out sufficiently small and dense stars can still be difficult to distinguish from black holes. So far, the best we can do is to say that the radius of the black hole candidates we see in the universe is at least approximately equal to their Schwarzschild radius. In some cases, that's just a rough estimate, but in others, we've calculated that radius to within observations of massive black holes showed them to be growing in mass over time at exactly the same rate that dark energy would be expected to grow over time due to the expansion of the universe. They came to the inevitable conclusion that black holes must be made of dark energy, and that they are really more like gravastars than ordinary black holes with infinite density singularities at their centers. This conclusion was fiercely contested. Astronomers came out arguing that the analysis of the observational data wasn't quite right, and theoretical physicists came out arguing that the expansion of the universe should have nothing to do with the growth of black holes in any case. So while the idea that dark energy could exist in the form of gravastars sounds exciting, it looks like the scientific community isn't going to be convinced unless it's simultaneously supported by better data and more compelling theoretical models. So while gravastars may exist, we are far from proving them. And they might look too much like black holes to be able to easily spot in the first place. But the next exotic object I'll explore today should be as recognizably distinct from a black hole as it's possible to get. They are black holes' opposite, the push to a black hole's pull. They are white holes, and there's no reason in physics why they couldn't exist. I want to start off with a simple analogy. If I ask you to imagine a cone, you'll probably think of either something that points up, like a traffic cone, or something that points down, like an ice cream cone. These are what we think of as cones in the real world. But if you write down the most general mathematical equation for a cone and try graphing it, you'll get something that looks like two cones glued together. You see, a mathematical cone has two halves, one that points up and one that points down, connected at their tip.